Hello everybody, welcome to 6-6 Exponential and Logarithmic Equations. Today we are going to learn to solve exponential and logarithmic equations using a common base. We're going to solve exponential equations using logs, and then we're going to solve exponential and logarithmic equations using graphing. Alright, so first of all, let's talk about finding a common base to solve. Because essentially, let's look at this property of equality for exponential equations real quick to talk about what we're about to do. If b to the x equals b to the y, then x equals y. In other words, if we have two sides of the equation, each of which have the same base, then we can actually kind of ignore the bases and just set the exponents equal to each other. And the reason why that would be useful is, let's say the value we're trying to find, in other words x, let's say x is in our exponents, right? If x isn't in any way in our base, we don't really need these bases anymore. We kind of just want to solve for x, right? So if x is in our exponents, we can rewrite the bases so that the bases are the same. That way we can just evaluate the exponents to solve for x. So let's go ahead and do a problem here, right? Let's talk about this. So if we have the question 1/2 to the x plus 7 equals 4 to the 3x, how can we rewrite the bases to solve this? Well, first of all, it's important to figure out, can 1/2 and 4, can we rewrite those to have the same base? And in this case, we can, right? Because 1/2 is the same as 2 to the negative 1, and 4 is the same as 2 squared, right? So 2 to the negative 1, we can replace 1/2 with 2 to the negative 1, and we can replace this 4 with 2 squared, right? So then what you'll get is you'll get 2 to the negative 1 to the x plus 7, right? And then 2 squared to the 3x, right? So now, if I distribute this negative 1, I get 2 to the negative x minus 7 and 2 to the 6x. And now you'll notice that both of these pieces have the same base. So according to our property of equality for exponential equations, we know that negative x minus 7 has to equal 6x. Now, the hardest part of this problem is probably this first part, right? Rewriting to a common base. And that's just something that you're going to have to do with experience. You're going to have to practice some of these. Remember that anytime you have a fraction, you should be looking for a negative exponent, right? Just to see if it's something that you can do, because this will save you a lot of time. It'll make a lot of problems very trivial, actually. All right, so now we can finish solving this. It's just going to be basic algebra from here, right? We have 2 to the negative x minus 7 equals 2 to the 6x. Remember, the exponents we can set them equal to each other because the bases are the same. So now we have negative x minus 7 equals 6x. Simply add x to both sides. You'll get negative 7 equals 7x, which means x equals negative 1. All right, awesome. So let's go ahead. Let me give one for you guys to try right here. Just this part at the very bottom. I already kind of did some of the math here, so I'm going to let you pause the video now, and we will jump back into it together. All right, so if you want to skip ahead a little bit, if you got x equals negative 2, you're good to go. If not, let's go ahead and talk about how we can do this together. So we have 25 to the 3x equals 125 to the x minus 2. Now, hopefully you recognize that 25 is 5 squared, and 125 is 5 cubed. This was last unit where I talked about, we really need to start knowing at least the squareds and the cubes, right? We need to know what these values are. We should recognize quickly that 125 is 5 cubed. If not, this is something you really just kind of need to go back and memorize. Just like you needed to memorize times tables, right? This is the exact same idea. If you get behind in this element, then it's going to just make every other thing that you do going forward more and more difficult. So please, at least with the squareds and the cubes, and maybe some of the to the fourth power, you know what I mean? Some of the fourths, please get these down, right? At least through 9, right? 9 or 10, just like you did with times tables. It's just going to make your life a lot easier. All right, so 5 squared to the 3x equals 5 cubed to the x minus 2. Now that we have the same base, we can ignore the bases. So we have 2 to the 3x equals 3 to the x minus 2. Distribute the 3, distribute the 2, right? Well, it's not really distributing the 2, but anyway, 6x equals 3x minus 6. You'll subtract 3x from both sides, right? And then you'll get 3x equals negative 6. Divide by 3, x equals negative 2. All right, so the key steps are identifying that this is 5 squared and that 125 is 5 cubed, and then realizing that because the bases are the same, we can set them equal to each other, and then it's algebra from there. All right, now one of the goals of this lesson is going to be able to use logs in a useful way, right? Up until now, we have found uses for logs, but the entire purpose of a log is that if you have an equation where you have a variable in the exponent, we don't have a way of solving for that, right? If you have 3 to the x and you're trying to solve for x, what are you going to do? Take the xth root, right? Like if you're 3 to the x, if you're taking the xth root, that's not going to get us anywhere, right? We need something that we can use to get numbers out of the exponent so that we can actually solve for them, right? So if we have like x in the exponent, or we have our variable that we're looking for in the exponent, logs are what we can use to kind of negate that. Just like we use division to negate multiplication, and we use subtraction to negate addition, right? Logs are what negate exponents. And that's what we're going to talk about in this lesson, is I'm going to really show you how to do that. So first, let's talk about rewriting exponential equations using logs. All right, so if we have the problem 17 equals 4 to the x. Now, this concept here of rewriting with common logs, this is the reason why we're allowed to do this. You don't want to do this every time in every problem, right? You don't want to rewrite this as 10 to the log 17 equals 10 to the log of 4 to the x, right? You don't have to do this every time, but I'm just showing you why this works, right? Because if we were to rewrite this, right, log 17, this would have a base of 10, right? And then log of 4x, 4 to the x, this would also have a base 10, right? And if you note down here, I kind of explained it. This might be more confusing than helpful, but this is just me trying to show you why we're allowed to do this. Note that base 10 of log base 10 of x, this is the same thing as x. This log base 10 of x and with a base of 10 is that all of this is the same as x. This is the reason why logs work, right? So we can rewrite 17 equals 4 to the x as all of this, because they essentially would cancel each other out. If you want to go back and actually check the math and like go through this, you can, right? And you'll see what I'm talking about. So what we're going to do is now we have 10 to the log 17 equals 10 to the log of 4 to the x, right? Because these have the same base, we can basically ignore the bases, right? So all of that said, right, the idea is that if I take the log of both sides, right, I know it sounded like a lot, but it's really important for you to understand why we're allowed to do this, right? We're taking the log of both sides so that way we can get this exponent out of here, right? This x as an exponent is not going to, we can't do this. We can't do anything with this. So we need to use logs. And that's the point of logs this entire time, right? Is so that we can learn this, so we can get here. Yeah. So we have log of 17 equals log of 4x, right? So if we come down here now, you can kind of see this is where we're getting to. If we take the log of both sides, log 17 equals log of 4 to the x. Now what's cool is because we have a log of 4 to the x, remember our power to a power in terms of logs, we can bring the x out front, right? So that's what we're going to do. So we're going to have log 17 equals x times log of 4. Well, if we're trying to get x by itself, which is the whole point, we would divide by log of 4, right? So log of 17 over log of 4 equals x, which equals about 2.04, right? So the point is, if we take the log of both sides of this, we can take the exponent out, or we can take the variable out of the exponent, and then we can like actually solve for it. All right, so let's go ahead and move on up here. Let's give this a shot. All right, so solve exponential equations using logs. I already explained this middle step is unnecessary, right? I kind of explained why we're not going to do this. So for now, I'm just going to skip past this. But you can see I put this in here just to show you that this is what we're doing. So if we have 3 to the x minus 1 equals 5 to the x, well, it's going to be a little bit more tricky because, first of all, we have x's on both sides, but it's just going to take more algebra. We can figure this out. So I'm going to take the log of 3 to the x plus 1 equals the log of 5 to the x, right? So let's do that first. And now, of course, we can bring these exponents out front. So this would be x plus 1 times log of 3 equals x times log of 5. And if it helps you to think of it as, right, if you think, because we're going to end up distributing this, right? So if you want to think of this times as like this, right? If this helps you Think of it as like, okay, it's this times this. Because if we have x plus 1 times log 3, this is x times log 3 plus 1 times log 3, right? Like these would have to distribute to this. And that's actually what we're going to do in the first step, right? So distribute x plus 1 to this log base 3, or this log of 3, right? So we're going to get x times log of 3 plus 1 times log of 3. And of course, 1 times log of 3 is just log of 3, right? Because it's times 1. So we're going to, this is the whole point of this is that we're going to rewrite this here. So we have x times log 3 plus log 3 equals x times log 5. Of course, we brought this x out in front also, right? Up here, we brought this x out. So we need to get x's on the same side, right? So if we have x times log 3 plus log 3 equals x times log 5, I'm going to take this x times log 5 and move it to the left, and I'm going to take this log 3 and I'm going to move it to the right, so that way I can get the x's on the same side. So when we do that, we'll get x times log 3 minus x times log 5 equals negative log 3, or negative 1 times log 3 is really a better way of looking at it, right? So all we did was we subtracted this and we subtracted this, and it kind of simplified here. All right, now this is kind of a key step too, right? If I have x times log 3 minus x times log 5, I can actually factor out an x from each of these, right? If I had an x times this and then x times this, I can factor out that x. So that's what we're going to do. So we're going to factor out the x, and that's going to leave us with log 3 minus log 5, right? And then, of course, that's going to equal our negative 1 times log 3. Now we have x times all of this equals this, so we can divide by all of this, right? And that'll leave us with just x. So if we divide both sides by log 3 minus log 5, right, which is what we do down here, then we can set everything equal to x. So our final answer will be x equals negative log 3 over log 3 minus log 5. And this we can put into our calculator, right? And if we put that into our calculator, we get approximately 2.15. So is every problem that you're going to have, is every problem going to be this complicated when it comes to the algebra? Well, no. But if you just replaced all of these, if you replaced all of these log 3s and log 5s and all this stuff, if you replace these with just numbers, you would know how to do this, right? This wouldn't even look complicated, actually. This would look pretty simple. And what I'm saying is, like, we can use a lot of the same algebraic rules on logs, right? So all I really did was I distributed first. And remember, like I said, if this was a number, if log 3 was a number, you wouldn't think twice about this. If this was like a 2x, right, you would do x times 2x, and you'd do 1 times 2x. And then you get your binomial, right? And it's the same thing down here. If this was like x, times like 2x plus 1, right? Or if this was like, if this was x times 2x minus x times 1, right? You'd realize that you can pull out the x, right? It's the exact same idea, right? The only difference is that now we have the word log attached to it, so it looks more complicated. But it's the same rules we used before. All right, so, and by the way, this is just, if this seemed a little bit tricky to you, which is completely understandable, right? It looks more confusing than it is, like, that's what I'm trying to explain, but it's just going to take some practice, right? You're going to have to run into situations where you have to use the distributive property on logs, right, in order to actually, like, understand how this works. So you're going to have to do a couple practice problems of these to kind of get the hang of them, but they work exactly the same as every other algebra does. That's what I'm trying to say is, like, don't be too scared going into it. Just think, if these were numbers, what would I do? All right, so solve logarithmic equations. Now, let's talk about the property of equality for logarithmic equations. If we have log base b of x equal to log base b of y, then x equals y. And it's actually the exact same concept as before, right? Because if we're establishing that these are the same base, then of course the results are the same, right? We already know this. But if it has the word log in front of it, right, we want to make sure that the rules are the same. So this is kind of what it is, right? If we have two logs with the same bases, then the results will equal each other. So if we look at our problem again, right, we have the ln of x squared minus 16 equals the ln of 6x. Well, remember we just said, right, the ln's are always going to have the same base. This is technically a base e, right? So if we have the ln of e of this equals the ln of e of this, then these two things equal each other. So in other words, x squared minus 16 equals 6x. And now it's just a quadratic problem, right? Because now we're going to move the 6x over so we can set it equal to 0, right? We'll get x squared minus the 6x minus 16 equals 0. Now it's a trinomial factoring situation, right? What multiplies to get negative 16? That adds to make negative 6. And of course, this is negative 8 plus 2, right? And now we have x equals 8 and x equals negative 2. Because we set these both equal to 0, right? X would equal 8, x would equal negative 2. So we have our two answers here, right? Which makes sense because we have a quadratic, right? We should have two answers. Now what we have to do, just like always, anytime we deal with square roots, we're going to have to check for negatives, right? Or we're going to have to check for extraneous solutions. In this case, our logs can't be negative. And I'm going to go into this in a little bit as exactly why. But if the result inside a log, in other words, the ln of this number, if this number is negative, then we have an imaginary number, right? The result can't be negative because then we'd have to take out an I in order to make it result, right? So what we're going to do is we're going to plug in our answers for just this ln result part, and we're going to see if they become positive, right? So if we take our 8 first, we'll have 8 squared minus 16, right, which is 64 minus 16, which is 48. So here we're going to have the ln of 48. And then on this side, we have the ln of, well, it was 6x, so 6 times 8, right, which is just 48. Now, these will equal each other, right? We already knew these were going to equal each other. It's another way of checking your work, I guess. But the thing that we really care about for this part is, are these negative? Well, 48's not negative, 48's not negative, so we're good. But what about negative 2? And usually it's negative numbers you got to be careful with, so let's give it a shot. So if I go here, I have 8 squared minus 16, right? Well, this 8 is going to become negative 2. So it's going to be negative 2 squared minus 16. Negative 2 squared is 4, but 4 minus 16 is negative 12. So this is negative, so this isn't going to work. But let's check, see if we did the math right. I mean, we already know, but okay, so this was 6x. So now we have 6 times negative 2, which is negative 12. So, I mean, we did the math right? This is equal to each other, but this will be an imaginary number. And we'll reference back to this here in a second when I talk a little bit more about this, but this is you have to double check for this, right? Just to make sure that we're not using imaginaries in our answers. Okay. So, solve by graphing. Always a fan favorite. All right, so let's, like before, right? We've been solving by using logs, right? And there's going to be a lot of situations in which solving with logs are very useful. But if we get an equation that looks like this, anytime you have a function equals a function, you can graph both of those functions and find out where they intersect. That will always work. Okay, and that's exactly what we're going to do here. We're going to look at this as a system of equations, just like you learned in Algebra 1, right? So we have log of 2x plus 1 to the 5th equals x minus 2. Now, the only thing you're going to have to do for this, right, to make sure that when you graph this that it comes out properly, is do you see this 2x plus 1 to the 5th? You want to be careful about what you're doing with this exponent. So really what you should do is you should bring it out to the front. And I'll actually rewrite this and show you what I mean. So we want to take this 5 and move it out front. So we should rewrite this as 5 times log of 2x plus 1. Right? We should rewrite this like this because the calculator will always read this accurately, whereas sometimes it won't read the other one as accurately. Okay, so if we put this into our calculator as 5 times log of 2x plus 1, and then we graph the other function as x minus 2, right, we'll get this to work. So like I said, over here, I wrote that we're just using this equation, which we technically are, but like I said, this one you will want to rewrite by pulling the 5 out in front, or it's going to sometimes give you some really, really funky things, right? Just trust me on this one. Always rewrite your exponents out front. It'll make your life a lot easier. All right, and then we have y equals x minus 2. So I've already done this, so let's go ahead and pull these up. So 5 times log x, or 2x plus 1. Actually, let me just show you this real quick. So if I have log of 2x plus 1 to the 5th, right? So let's just compare the red to the, I'll make this like I don't know, orange, whatever, it doesn't matter. Do you see how much different these are, right? Do you see how the graph does really weird things? And all I did was graph exactly what the problem said, right? Log of 2x plus 1 to the fifth, log of 2x plus 1 to the fifth. But you see how off this is, right? That's because the calculator is, like, it doesn't understand this exponent part. I'm telling you, I've done this a bunch. It's literally just, if you move the exponent out front, it works. Okay, so let's actually, we can just get rid of that. I was just kind of showing you that just for fun. All right, so now we have our two functions, right? We have 5 times log of 2x plus 1, and then, of course, x minus 2. And now, what are our answers for x? Well, where do they intersect? We have a negative 0.3289, right? And then we have 8, is that right? 8.2, right? Okay, so we go back here, right? We have our two answers, right? The negative 3.29 and then the 8.204. Perfect. Both rounded to 3 decimal points. The problem will tell you, right? Okay, so we graphed them, we found x. Now what do we have to do? We have to check and see if they're correct answers. Now, remember before I told you that the reason we're doing this is because we can't have a negative inside the log, because then we could get negative, or we could get imaginary numbers, right? If we go back here, are either of these answers imaginary? No, they're on the graph, right? So we don't like when you graph, you know that these are real answers. So yes, you can go back and check the math, right? And I will show you that I did this. And if you want to look at it, right, you can, right? I solved that this would be the log of 0.342 to the fifth, which any raised exponent of a whole number or a positive number is going to give you a positive. So this will work. And then down here, this number is very positive, right? So it's not even a decimal. It's actually like a full number. So yeah, both of these work, right? As evidenced by the fact that you can see them on the graph, right? If they're on the graph, they're real, right? So we're good. But just remember how before I told you that this one doesn't work, right? And we did the math and we put the stuff in. So what I did is I did this function and I took the original pieces here, the ln of x squared minus 16 and the ln of 6x, right? And I went ahead and graphed these just to show you. Okay, boom. We have a purple. I'm going to change this purple to a orange because I think it like sticks out a little bit more. Okay, so you'll notice that we have one intersection here, right? We can zoom in a little bit. We have one intersection, and it's at 8, right? X equals 8. What about negative 2? Well, what about negative 2, right? Look at this. It looks, these just kind of end. I don't know if that's actually the way it should work, to be honest with you, or if it's just a computer thing. But either way, x equals negative, or let's just put in x equals 2, just to show you, right? That's this red line. Does the green line ever intersect with the red line? No, right? So it doesn't work. It's imaginary. The intersection of those two things at x equals 2 isn't real, right? So this is just me kind of showing you, yes, 8 works, right? 8 seems to work just fine. Negative 2 does not. Oh, I put in 2. It's the same idea, right? I put 2 instead of negative 2. That's my bad. But it's going to do the same thing, right? You're not going to have anything there. So just to recap, right? Because this lesson was, there was kind of a lot. It was very dense, right? There wasn't a lot that we learned, but the stuff that we did learn was quite, it can be quite challenging. So it's just going to take a lot of practice, but it's something that you can do. I'm sure of it. So first we talked about finding a common base to solve, right? We rewrote this with a common base, and then we solved, right? We just kind of used basic algebra after that. Rewriting exponential equations using logs. This is the bread and butter. This is actually what we use logs for. We use them to get variables out of the exponent. And that's what we did, right? So this was just telling us how to rewrite it. We then did a problem with some rather complicated algebra, but the setting up of the problem itself wasn't too bad, right? If we have 3 to the x plus 1 equals 5 to the x, we can take the log of both sides to get those exponents out. And if you understand that concept, the rest is just you understanding algebra a little bit better, right? And hopefully that can at least be a little bit of a hopeful glimmer for you if that was a bit challenging, right? When you go into the problems, at least set it up right, and then the algebra can be the part that you work on. Does that make sense? All right, and then we solved logarithmic equations, which is the exact same idea. If you have two logs, with the same base, then the results of those logs are going to be equal to each other. And then we solve by graphing, which is by far the easiest. Create a system of equations, where do they intersect, check your solutions, and all that. All right, so this was lesson 6.6. Next up is lesson 6.7, which is where we get into geometric sequences and series, which is very, very challenging. It's probably the most challenging thing we're going to do all year, besides maybe trig. So put on your thinking caps for that one, and I will see you there.